work energy theorem. Okay, so now next one is all about your work energy theorem. This is also plays a major role in this chapter. So in order to understand what exactly the work energy theorem is, we have to consider a body of mass m. So let us consider a body of mass m moving with initial velocity u. So let us consider a body of mass m is moving with velocity u, initially moving with velocity u. Okay, and now when an external force F is applied on it, when an external force F is applied on it, then what happens, children? Whenever an external force is applied on this body, initially it was moving with velocity u. When an external force is applied, then what happens? Mass can never change. So what can change? Its velocity. Body gets accelerated. So whenever force is applied on it, the body gets accelerated and as a result its velocity changes. So for the same body, whenever the force is being applied on the same body, then its velocity changes to v. Earlier it was u. Because of the application of force, its velocity is changed to v. Are you getting me, children? Well, so then its velocity changes to v. That's it. So consider a body of mass m moving with velocity u. Whenever an external force F is applied on it, its velocity changes to v. Okay. So now let us see what happens. What is the initial kinetic energy, children? The initial kinetic energy of the body is half m u square. Formula for kinetic energy is half mv square. But what is the velocity? Mass into velocity square. Velocity is u. And the final kinetic energy of the body is equals to half m. Final condition, what is the velocity of the body? V. So v square. Earlier it was half m u square and now the final velocity is, final kinetic energy is half m v square. So do you observe any change in kinetic energy? Yes, of course. So the change in kinetic energy equals to final kinetic energy minus initial kinetic energy. So what is the value of final kinetic energy? Half mv square minus initial kinetic energy is half mu square. Okay, children. So what is that? Final kinetic energy minus initial kinetic energy. Half mv square minus half mu square. After simplifying, we have this delta Ke is equals to both the relations. We have half and half m and m as common. So taking out half and m common, you are left with v square minus u square. But from the kinematics equations, third kinematic equation, we say that v square minus u square is equals to 2as. As whenever force is applied, you know that the body accelerates. Because of the application of force, the body gets acceleration. What acceleration? A. So v square minus u square equals to 2as, or the value of s can be written as v square minus u square by 2a. So what is the value, children? S is equals to v square minus u square upon 2a. Okay. Hence, this can be written as, I'll just leave it here, children. V square minus u square can also be written as 2as. What is the value? V square minus u square. From the kinematics equation, we know that v square minus u square equals to 2as. Substituting the same, we have the change in kinetic energy equals to half m into, that can be replaced with 2as. Simplifying further, this 2 and this 2 gets cancelled. And now you are left with change in kinetic energy equals to, what is left over? M, A and S. So let me just keep it here. So change in kinetic energy equals to Ma into S. But what is Ma? We know that the force applied on a body is equals to product of mass and acceleration. So Ma can be replaced with force. So delta Ke is equals to F multiplied with S. But what is Fs? Fs is nothing but work done. Hence the change in kinetic energy is stored in the form of work done. Hence we conclude that the work done is stored in the form of change in kinetic energy. Work done is stored in the form of change in kinetic energy. This is an important relation, children. Very, very important. So work done is always stored in the form of change in kinetic energy, and this leads to work energy theorem. So what we have considered? We have initially considered a body of mass m moving with initial velocity u. Whenever a force is applied on that body, the body starts accelerating. As a result, its velocity changes to v. Now initial kinetic energy is given as half mu square, whereas final kinetic energy is given by half mv square. We observed a sort of change in kinetic energy. So in order to calculate the change in kinetic energy, delta Ke equals to final kinetic energy minus initial kinetic energy. So Kef minus Kei. Final kinetic energy replaced with half mv square, initial kinetic energy replaced with half mu square. Taking out half m as common, you are left with v square minus u square. But from the kinematics third equation, we know that v square minus u square equals to 2as. Substituting the same, 2 gets cancelled, you are left with mas. But we know that from Newton's second law, F is equals to ma. So let us replace ma with F. Then delta Ke, that is change in kinetic energy, is found to be F. S, and Fs is nothing but product of force and displacement gives you work done. Okay. Hence, change in kinetic energy is stored in the form of work done, or work done is stored in the form of change in kinetic energy, and this leads to work energy theorem. So with this, on this concept, whatever we have gained, children, let us try to apply the same in the solving the numerical part. So let us move to the numerical part of this work energy theorem.